And so our first lecture on finite element, just like our first lecture in finite volume, is discussing conservation laws. Our first lecture in finite element discusses the weak form of partial differential equations. So remember, in finite difference, we are looking at the differential form, the form of the equation involving all the spatial derivatives. In finite volume, we're looking at the form of the equation that is integrated over a particular volume. So we are looking at the integral form. Because we are sticking to conservation laws, after the volume integration, the spatial derivatives disappear. What we get is the integral of the flux over the boundary. So we use that form to construct finite volume schemes. In finite element, we start our discretization from yet another form of the differential equation. It's called the weak form. Okay. In order to explain what the weak form is, I need to first explain a concept called projection. Projection is perhaps the most important concept in finite element, because like practically everything we do is a projection. So let me go back to MATLAB and close this file, and let's clear the terminal. I'm just going to remind you the difference between finite difference, finite volume, and finite element. In finite difference, when we draw a function, what the computer remembers is the value of the function at the grid points, right? When you do finite volume, when you draw a similar function, what you remember are the volume averages. So today what I'm going to do is I'm going to have two demos of different finite element methods, and I'll ask two people to come up and draw a few functions, and through drawing these functions, I want you to start trying to guess what finite element is doing, what kind of approximation is finite element doing to the functions you draw. Okay, anybody wants to come and try? You can draw as many functions as you want and try to figure out what finite element is doing. Yeah, please.
Whatever function?
Whatever function, yes. Oh. Just close this window, yeah. All right. Yeah, you can take a look at the function, and can you tell us what computer has done to your function?
Well, the approximate each piece is a linear function. This is straight line.
Yeah, the computer is approximating the function you drew, which I think you can still see that as the faint red line over here, with a piecewise linear function, right? But what piecewise linear function is it? Like, how is the piecewise linear function an approximation of your original function? Huh? Okay, what you said is the area under the curve seems to remain the same. Yeah, I'm not entirely sure. Yeah, every line seems to also cross the original function, right? And also, so the area under the curve remains same. Is that a I don't know if that is true or not. I can't figure that. I can't construct a counterexample. I can't prove it on top of my head. But that's not what finite element directly tries to do at least. And maybe what you said is true. Does somebody else wants to come and draw some other functions trying to figure out what this is doing? Yes, please. Let me close this one for you, and please. Oh, sorry. I think you need to start from inside this. If you start from outside, that's another thing we may want to improve in the future. Wow. Okay, thank you. Again, it's a piecewise linear approximation, right? But exactly what does it do? Okay. Uh-huh. Right. Yeah, it is not entirely clear what it does, and let's keep this mystery a little bit further, and maybe we can figure out by looking at a slightly different type of finite element. Let me call DG demo. It's another type of finite element, but like with a different linear space. Let me say. I'm going to explain a little bit later. So somebody else come on and try this second type of finite element to see if you draw some function, how does this approximate? Yeah, please. And maybe piecing all both of these pieces together, we can figure out what finite element actually is doing. Okay, we get another function. Thank you. So now, finite element is approximating the faint red function you drew with that thing. What is that? Again, it's a piecewise linear approximation, but now it allows itself to be discontinuous at the boundaries, right? And what is the commonality? So that's the difference, right? But what is the commonality? What is of course it's piecewise linear. What do you think finite element is trying to do? Yes? Average slope. Yeah, that's probably also right. Okay, yeah. The area between the curve and the linear line is minimized. That's getting very close to the point. Yes. The integral of the difference squared is minimized. That's actually coming to the truth. So yes, you are correct. If you visually look at this a little bit further, okay, and imagine there is a string, like there is some kind of elastic string or spring between the continuous function and the piecewise linear function. At every single point, there is basically a huge number of strings around them and pulling them close to each other. While these piecewise linear lines, they are sticks that cannot be bent. And this is going to be what the shape is going to be. It's kind of all these strings pulling each other. And as you said, it is the correct solution for that, like the collection of string problem is actually minimizing the total energy of these strings, which is kind of the elastic energy is proportional to the square of the distance. So that's actually right. And similarly, in the previous case, it's actually the same if I draw a bunch of strange functions, okay? It's actually the same, except for the sticks are actually connected. They are not allowed to break from each other, right? So in both cases, we have a type of minimum energy approximation. We have an approximation that is of course restricted, right? It is restricted in this case to be continuous and piecewise linear functions, and in the previous case it is restricted only to be piecewise linear functions without having to be continuous. But in both cases, we are constructing the best approximation of the original function, and best in the sense of minimizing the integrated squared distance from the original function and this approximation.